So we're ready to get going. It is with great pleasure that Mr. Adam Cohen is joining us on a trip to Toronto, and he's going to talk for an hour or so about his adventures, passive house and commercial buildings, which usually everybody thinks passive house and residential buildings. So he's going to talk about that other side of things where people don't really think we travel in terms of passive house and commercial buildings. Adam is trained as an architect, obviously certified passive house consultant. The real fun part, the part that I always smile about, is he's a builder for many, many years. Pretty much, I would say, all your life. It's a family thing. And so he brings a unique background of actually knowing how to do things and also knowing the academic side and the theoretical practical side as well. So, without further ado, Mr. Adam Cohen.
I appreciate you guys being interested in this. I pretty much go around the U.S. evangelizing about passive house, and so I kind of cobbled this together at the last minute. So there's disparate slides from different presentations. So excuse me if it's a little disjointed. I wasn't sure what people were kind of levels of interest, but we'll just go ahead and start right into it. And I thought, first of all, you guys probably want to know, like, who's this guy that he brought in here? I'm a guy that kind of grew up. If anybody recognizes these people, Ken Cohen, he was a underbuilt homestead type person, and Gaudi, of course, and Malcolm Wells. These are the people that I was into as a high schooler. Otto Fry, or Fry Otto, and Sarah and Michael Reynolds. So do people recognize these people? Is there anybody getting this kind of stuff? I do. Kind of. Okay. Well, you know, they all have certain things in common, that they're into natural forms and natural form design, etc. And that's just because I wanted to be a sculptor when I grew up, and I still do. These are some of my work, but it's hard to raise a family on sculpture, so most of these just sit around in the house. So what happened was I graduated in the early 80s from University of Maryland, and I immediately went out and started building these kind of recycled houses that were what I call healthy homes, off-grid homes. I've got people that have been living in houses 28 years, never paid an electric bill. You know, we built these homes with, you know, composting toilets and conserving energy, and there was no such thing as green, right? I mean, it was all just you know, a bunch of people up in the mountains trying to live back in the land. And we kind of put our buildings together with spit and bubble gum, and we had various success. But for me, after 10 years, I had a family of 5, and I was making no money, and I realized I probably needed to do something else. So I started a company called Structures Design Build, and we started doing kind of more traditional design build, right? So we do residential, commercial. These are all some examples of our work. And it's you know, became kind of a successful company. We had 42 employees before the economy in the U.S. went kaflooey. We have 14 now. But what happened to me is, 2006 or so, we were sitting at the dinner table, and my middle child said to me, "Hey, Dad, how long have we known about global warming? We're learning about global warming in class." I said, well, you know, back in the 70s, we talked about ecology and the earth, and not really global warming, but, you know, and we started kind of going into that, and he said, he just looked at me with one of those, like, innocent 12-year-old kid faces and said, "You mean people have known about this 40 years and haven't done anything?" I mean, just like, and it felt like somebody just slapped me in the face, and I realized that going from what I really was passionate about to this was really selling out. And so I started saying, well, I got to, you know, do something if I just make money, right? So I started looking around, and that's when I discovered Passive House in 2006. And I started realizing that these guys actually figured out what we couldn't figure out back in the early 80s. I will admit that I'm one of those people that bought into the whole super insulation thing back in the early 80s. I'm also one of those people who had to go back and fix my super insulated houses because they started to melt because I didn't understand the building physics, right? And you know, as Dr. Feiss says, you know, Dr. Feiss is the founder of Passive House. He says, you know, Americans are cowboys. They just go out there and build. They don't think, right? So the Germans think. And I couldn't believe it when I started reading about their work. It was like, it became obvious to me that they actually had figured out how to do what we couldn't do, or at least I couldn't do. And so I bugged Katrine Klingenberg, who's the head of the Institute in the U.S., and in 2006 I found out she was starting the Institute, and I said, I've got to take classes, or where can I learn about this? She said, oh, we'll give classes. Well, it was a couple of years later they finally gave classes, and I was in one of the first classes to do Passive House. And this is a project that we built, we'll talk about a little bit later. It's the first public school in the U.S. It was a prototype project. Showed off a lot of different construction techniques. This is a student center at Virginia Tech. It's the Malcolm Rosenberg Center for Jewish Life. It's 8,000 square feet. It's the first mixed-use assembly building being built to Passive House standards in the U.S., and that's under construction right now. This is the dental clinic. We're working with PHI in Germany on this one. This is a prototype building. They haven't done a dental clinic to Passive House standards, so we're working with them to figure out what the best practices are for a dental clinic, and this is a dormitory building that we're working on currently. So, when I discovered Passive House, I realized very quickly that Passive House was what we needed, right? It took me about, probably 2 or 3 articles, and I realized that they had found, or the Germans were able to synthesize a lot of the work, or amalgamize a lot of the work that has been done in low energy design for the past 40 years, and really put it into a very accessible and very logical package that made it very that made it so that it could actually, that low energy buildings could actually be designed and built reasonably, cost effectively. And as a design builder, as somebody who actually, we design what we build and build what we design, right? So as a design builder, I recognize that commercial construction made a lot of sense, right? So we all know that what's going on in the world is things are changing, and they're changing really fast. Like in your guys' generation, all this is going to happen, right? We're seeing it now. In the U.S., our climate zones have all changed. I'm one climate zone warmer now. Yay. So my camellias were blooming on the way when I came up. It was crazy. But I believe that we can actually make the shift. I don't know that we will make the shift, but I do have that belief. And hopefully you guys, as designers of energy-consuming monsters, will believe that too. So, where are we going? I think it's incumbent on us as designers to think about energy as an integral part of everything we do, anything that we approach. We need to be thinking, because whatever you build is going to be here for 50, 100 plus years, right? So what you build today is going to be taking energy from your grandchildren, right? So we need to think about that. So I threw this in because I didn't know what level of Passive House understanding there was, so I'm going to do this very quickly. This is what Passive House is not. It's not a 1970s passive solar house, right? Probably the worst part of Passive House is the name for the U.S. and North American audience. What it is an integrated design system based on building physics. It's all numbers. There's no prescriptive anything. There's no point categories you got to click. There's no build your wall to an R19. There's no anything like that, right? It's just about building physics and making sure that your balance is correct. And the nice part about it as a designer is that it allows you ultimate flexibility in your design. You have no restrictions except for very few parameters that you're trying to meet. So as creative as you can be is the only limit to your imagination. So to be a Passive House, what do you need to do? Well, and you have to have annual heating or cooling demand of 15 kilowatt hours per square meter. And that's based on net floor area. That's a German definition. Russel can go into those details if somebody really cares. You have to have an annual total primary demand of 120 kilowatt hours per square meter, and this is based on source energy. So like in my area where we're cold, we have to divide that by almost 3, so we get 40 roughly kilowatt hours per square meter, and that's a lot of times your limiting factor. And then the last thing is your air leakage at 50 pascals, pressurized, depressurized, is 0.6 air changes based on net volume of the space. And for those who may not know, that's a very, very tight building. We've been testing our buildings for 15 years with blower doors. When we build a building, if we hit 2 air changes at 50 pascals, and we only pressurized. We didn't depressurize, we just pressurized. We thought we had just knocked it out of the park. Like we had built the best building ever because we had gotten to 2 air changes. So when I was in fact in the class the first time, Katrina said 0.6 air changes, I was like, that's impossible. No way, you can't do it. Well, now we've got 6, 7 projects under construction, completed or not. We're regularly hitting 0.3, 0.4 air changes without too much trouble. So, it's very doable, actually. Now, what is the rationale? What is it so cool about Passive House? Right? Why all this buzz? What's all the excitement? Well, Amory Lovins kind of came up with this idea that there's a place in somewhere in the cost of super insulation and making a better building, you hit where you kind of hit a point where things become cheaper because your mechanical systems become smaller. And finding that point was one of these theoretical things that he pointed out, right? And this is not just in buildings, but in lots of other things too. And that's the sweet part of what Feist and Edmondson done, is they were able to locate the most cost-effective kind of point in the energy/dollar curve, and that's Canadian dollar, I assume, so it's probably worth a little more than American dollar. So right here is where the Passive House kind of comes in, right? And what you'll notice is when you insulate, as you insulate and you're increasing your costs, right? At some point you hit kind of a sweet spot where that mechanical system just drops out. And then you start, the more you insulate, you get a diminishing return. So this is the Passive House brilliance, really. Besides putting it into a form that everybody can kind of access, it was really focusing on cost effectiveness. And then probably, just as important is the simplicity of the standard based on just 3 metrics. So this is what's really cool. And having done this for 30 years, I understand the dollars and cents, because that's, I don't make any money unless we build it. We can design all day. If we can't build it, we can't make any money. So that's a lot of what this presentation is about. But that's a really important graph. And, I'm sure everybody here knows about the 2030 challenge. This Passive House is right in line with the 2030 challenge. We're regularly hitting a 70+% reduction in our energy without any site generation. So I'm going to hit this quickly. What are the advantages of Passive House? One thing is that we've got 100% outside air. So you guys all know the principle of the Passive House, hopefully, that we bring in outside air. We use an energy recovery ventilator or heat recovery ventilator to exchange the energy in that airstream. And so we're always breathing fresh outside through the air. So it's a bright, clear, open feeling to the building. For those of you who haven't been in it, you'll know it when you go into a Passive House. So you have this exceptional indoor air quality. The other thing is you have no more than a 4°C difference on any surface. So you have a very nice thermal comfort. You're not cold by the windows. Okay, it's the simplest way to put it. Your slab is not cold, right? Because of the building physics, you're controlling the surface temperature. And that's a very key thing. I think a lot of people, when they do their thermal equations for Passive House, they're all focused on on thermal breaks, thermal bridging, and they're not so much focused on interior comfort. And that's the other piece that I always push in the classes that I teach, is that you need to look at your interior temperature as much as your thermal bridging. So you have a nice thermal comfort in these buildings. It's a quantum leap in energy efficiency. This is what just blew me away. It's just 70% energy savings at a cost-effective method. I mean, it's just really amazing. Probably the best part for me in terms of the institute and the design performance, is that I'm able to take all my calculations and assumptions and designs and send them off to an institute where there's a bunch of other building geeks that'll look at it and tell me whether or not I made a mistake, or what they think, whether they think I'm going down the right path or wrong path. So, as a designer / builder who has to stand behind everything I do, having somebody to second check me is really great, and to challenge me and say, well, have you thought about this? Have you done that? That's a really great aspect of as a designer. So it's got this rigorous quality control and verification. We eliminate thermal bridges, as I just said, so, condensation, mold, all those type of things are gone. We don't have those. We have a much more robust building structure. And then the nice part is if zero energy is something that you're interested in, the first thing I learned when I did my first off-grid house was reduce first, right? Because the cheapest energy is that's not made. So, I mean, we used to, we were putting these buildings together with 75-watt Arco PV panels, which were like expensive 30 years ago. And, we're using VW batteries and spit and bubble gum and, like everything we could to reduce load, because you could only afford 4 or maybe 6 panels, and you had to have enough energy to use your inverter to run a washing machine for the diaper. So, you had to like pick where your energy went. So the nice thing is, having learned the lesson of reduce first, this is a really simple way to reduce first. So rather than producing a huge system, you're able to cut your system size by 60% to get to a zero energy building. So it makes the PV very much more affordable. I understand here you have an 80-cent buy-in tariff, so that's an argument that is harder to make probably here than it is in the States, but where I come from, PV has to stand on its own, there's no subsidy. So cost effective, zero energy, zero carbon. So those are all advantages of the passive house system. This was, I'm sorry about the slide, I was taken at a conference, but you can see here the exponential growth of passive house in Europe. By 2012, they're looking at about 70,000 projects being completed. So, and this, in 2009, the EU, after an extensive study, recommended passive house as the national energy standard for all member nations by 2018. Not all nations adopted as, quote, passive house, but that's German. They went on German. So, in Britain it's BREEAM, and in Switzerland it's Minergy, and they have different systems, but they're all based around this level of energy efficiency. And so, what's other things about passive house that maybe we don't think about, right, that are opportunities? Well, one of the things about passive house is that to reach these levels of energy efficiency, we need to think about building components in a different way, right? We can't really just build the standard buildings we've been building and expect much better results. So you get these new building components being invented. You get cutting edge window and doors, just stuff that performs head and shoulders above what certainly we have in the U.S. Innovative mechanical systems, we're seeing ERV and HRVs with efficiencies of 95%. Building systems that are simple, affordable, and groundbreaking. And what does all that lead to? That leads to the green jobs, right, that are promised but not around. Well, there's a huge opportunity for innovation in the materials science part and in manufacturing. In Germany, 15 years ago, they had 0 manufacturers of high-performance HRVs. They've got over 60 manufacturers now just in Germany alone. Right? In the U.S., we don't even have a window that's manufactured and that is a passive house certified window. It's a huge market. So I'm sure in Canada it's the same thing. That there's just a huge opportunity, a huge open market that's there to be grown. So in the U.S., and this is dealing with the U.S., we've got kind of 3 paths towards adoption, and that's what this talk is mostly about. We have the first, which is national legislation, which is the quickest and easiest way to adopt it, but as you guys might know, Washington is like severely broken, and so that is not going to happen. So the secondary way is our code adoption by state. So every state has to adopt an energy code, and that process, we use the International Code Council as the typical one. And in that, we have 3-year cycles. I think you guys use international codes too, right? Is that true? Like International Building Code, International...
5 to 6 years cycle.
Okay. Well, in the U.S., it's a 3-year. So right now, it's 2012. We're in the 2009. The 2012 edition is out, but it won't be adopted probably until 2015. 2015 won't be adopted until 2018, and 2018 won't be adopted until 2021. 2018 is the code cycle that is right now scheduled to hit passive house levels, right? So we're looking at maybe 9 to 10 years away where it'll actually be mandated, but the U.S. state system is just as broken as the national system. And by the time it makes it through the state legislatures, it gets watered down. And a lot of times you end up with all this BS coming out of the code. And it starts out with this great thing, we're going to make these passive house level buildings, and we end up with buildings that are, that the code basically lets you do pretty much anything you want, and it's watered down and useless. So to count on code adoption by state is probably not the best idea. So the third way is market adoption, right? Capitalist system, that's the way we got to go. So we've got to look at that German and European methodology of kind of the growth curve. And what we've seen in almost every country, and there's 47 countries now that have built passive houses, is that there's a small movement that starts, and over the course of the first 5-8 years, prototype projects get done. And for whatever reason, nobody wants to believe that building physics in their country works the same as building physics in another country. I don't know why it is. I mean, even they probably look down at the U.S. and say, well, your electrons turn the opposite way from Canada. I don't know what it is. But most, even like going from Germany to Britain, right? You would think that would be an easy step. Well, the British didn't want to believe it. But now they've got projects on the ground. They've got data supporting the fact that, yes, it's performing just like the other 20,000 projects are supporting. And now they're starting to climb that growth curve. And that's where we're going to be at some point in the future. And so right now, where I am way out on the edge doing the commercial stuff, but I feel certain that we are, we're here, but we'll get there. There's no question in my mind. So that's what I've been focusing on, is market adoption. So that's a quote from Wolfgang Weiss. Investing in value instead of energy consumption requires little financial efforts, but rather creativity and intelligent solutions. And that a truer statement was never said. Okay, so I wanted to hit residential, so I pulled this out of a residential presentation I had. Residential is different. Okay, that's a house under construction that they just moved in this weekend, actually. We're building our homes, where our company builds about 25% residential, 75% commercial, for cost parity with standard construction. Okay, so what does that mean? That means that most American families, and I would assume it's probably similar in Canada, they have a mortgage, and then they also have an energy bill, right? That's a monthly payment. You pay your mortgage, you pay your energy bill, right? Well, it's a simple choice then for us, because we have been able to deliver our passive house projects for the same monthly cost. The only difference is that you're either paying for electrons or you're paying for equity, right? So it's a real simple decision when you put it to a homeowner that way, and it becomes a no-brainer. I mean, it's all our clients now are building passive house, except those very stubborn clients that must have masonry chimneys. And once I figure out how to put those in passive houses, I'll win them over too, but I haven't quite figured that out yet. But I mean, if you're spending $1,000 on a mortgage and $100 on energy, and you can spend $1,060 on mortgage and $30 on energy, why would you not build it, right? Because you're building equity and paying the electric company. So that kind of problem in my mind has been solved. So the next thing comes this. This is what everybody the first initial understanding is that, you've got initial costs. In the U.S., I don't know about Canada, I don't know this mortgage, but in the U.S., everybody wants to focus on this lowest point right here. What is the lowest initial cost, right? So if there's a tiny little marginal increase to do passive house, right? And then you look at the operations and maintenance over time, that little bit of cost delta is eaten up in the first few years. And then after that, you've got this huge value that's going to deliver over time, right? And it's really been difficult to get Americans to talk about that. They always want to go, what's my break-even point? How long is it going to be? And I find that that's really a trap. It's not something we want to go to, right? So what we talk about is return on investment, because most of the people that we're dealing with, when I say me, I'm talking about the people that I'm trying to convince to build commercial passive houses. What they were dealing with are people that are owner-operators, right? So if I'm going to try to go to an apartment owner who's going to let the tenants pay the electricity bill, they don't care. They want to build the cheapest thing that they can rent for the most money. If it has less energy, they don't care. There's nobody connects with that. But if I find a that same apartment owner, but it's a university that's going to build a dormitory, and they have to pay the energy bills on it. Well, all of a sudden, they understand return on investment. You mean if I put in $100, I get out 10, right? So they understand it. They've been paying dorm bills for 40 years. So that's what I have been focusing on to sell and to market to my potential clients, is to demonstrate the return on investment model. So this is probably, I think this has the potential to be really groundbreaking in the U.S. This is Elm Hall on the Emory and Henry College campus. It was built last year, or 2 years ago. It was completed August 2010 as a modular construction, and it was built standard construction, and it was built with split HVAC systems in the lounges, and PTACs. PTACs are through-the-wall heat pumps like you find in hotels for all the rooms. And then they wanted to kind of go the next step up in energy efficiency, and they were going to put a huge geothermal system in. And we convinced them that passive house was the way to go. And I'll show you some comparative numbers here. So Hickory Hall is now under construction. It's virtually the same size, it's slightly larger, it's the same student population. So we're going to have a twin study, same construction technique, right? We're going to have modular construction, brick, same quad. So we're going to have the proverbial twin study. I mean, this could be real gold for the passive house movement, that we're going to be able to monitor and see how this energy performs, but we'll see here in a second. Here's some comparisons: 117 beds versus 116, 39,000 gross square footage versus 34,000. This one was built as LEED Silver. We're building this as passive house and LEED Silver. The budget for that building only, no site work, was $4.5 million, and for this is $4.73, so it's not that much difference. And the energy usage, you can see what our predicted energy usage per year. And you can see the comparison. I mean, it's really not that big, right? We went to, our above grade walls went to R29 from R20, right? That's not very different. We are roughly 50 in the roof versus R38, right? So really simple. The biggest change was the windows. I do a lot of what if modeling in my analyses, and if they had just taken that exact same dorm, and only changed to passive house certified windows, they dropped their heating demand by 25%, just by changing the windows. That's significant, right? And then there's some, they have raw outside air versus ERVs and the system type. We went from the PTACs and the split system to an integrated geothermal system, which we'll talk about that in a second. You can see here, look at the heating load. 50,000 BTUs total on the passive house, 570,000 BTUs for the Elm Hall. And we installed 142,000 BTUs. They installed 818,000. Okay, and interestingly enough, half of this goes to heat hot water for the showers. So, and this is so typical of mechanical engineers, right? Elm Hall, the design cooling load was 32 tons. What did they do? They installed 68 tons. I mean, there's a lot of reasons not to do that, right? One is a lot of upfront costs. Number two, you're going to short cycle your equipment by oversizing it, right? I mean, it's but that's how engineers think a lot of times. It's, well, if one is good, two must be better. And, with ours, you can see 14 tons, and we reinstall 14 tons. Why? Because we trust our numbers. We trust our energy analysis. And this is what we're predicting over code, 74% improvement. And we're about 60% improvement over Elm Hall. It was interesting, we did some analyses of plug loads, and I tell you what, trying to predict college students' use of plug loads in dormitory buildings is really difficult. But it's very critical for these type of high-performance buildings because a lot of heat gain can come off those plugs. But it was interesting when we did our analysis here, looking at how the energy was broken up in the passive house. We got 30% was going into plug loading, lighting appliances. But when we really started looking at it, clothes drying and clothes washing was over 50% of what they were doing. So it was really interesting to just look at kind of how the numbers all boiled out. So Just some quick statistics, 40,000 square feet, around the things. The investment, or the additional cost to go passive house, 230,000 American dollars. And what we did was we used for this comparison, we used the U.S. average kilowatt hour rate, which is 11 cents. I believe here, after tax, you guys are paying 15 cents after tax in Ontario. And the energy inflation, 30-year average for the U.S. is 2%. Of course, you know, energy doesn't go up 2% every year. It kind of stays flat as Jones. But when you plug those numbers into an analysis, what you find is, very first year one, you're getting an 8.8% return on your money. Put that in real terms. If any of the students have any money and they were going to go put it into a bank or a CD, how much money would you get back on that money from that investment? Right? I don't know, how much money would you get? Not very much. 1% maybe? 1.5%? 2% if you got a good one? On this, day one, they're making 8.82%. So I mean, for every $100 they put in, they get $8 a year back. They, year 2 or year 10, they're making a 10.5% return. By year 20, they're making a 12.85. Year 30, they're making a 15.6. And year 40, which you know the storm will be around 40 years, they're making almost 20% on their money by that time. Okay? And if you averaged it out, this is the annualized, and took all those savings and averaged it out, by the time they get out to year 40, that investment was worth 13%, meaning if they had pushed it all the way back to year 1. So what does that represent in terms of gross dollars? That represents to the school a savings of 1.2 million US. It's just not something to see that. And this is where you start really getting the attention of the really important people at universities, which are the treasurer type people, CFO type people. This is the Malcolm Rosenberg Center for Jewish Life. I wanted to throw this in. This is from another presentation, but just because it's got a cool system. This is a very complex building with a lot of different usage, and there's actually 4 different type systems in here. But the main part of the building that's being utilized 24/7, we've got a ERV, energy recovery ventilator. We're humid, so we have to use them. I know you guys use heat recovery ventilators rather than energy recovery ventilators here. But what we do is we supplement with solar hot water and with a passive ground loop, just a loop of pipe buried in the ground, no compressors or anything attached to it. And we heat, and then we pre-cool and pre-dehumidify before our ERV. Our calculations tell us that for most of the time, that half of the building should not require any use of this split system that is our secondary heat source. We found in the school that we built, we had similar calculations, told us the same thing, and the first 2 winters we've been through, our heat doesn't come on. We have enough solar hot water to heat. Just because what you got to imagine about a passive house, if you want to kind of picture it in your mind and get your mind around it in a simple way, it's a very big, one of those punchy clowns, you know, that's got the sand at the bottom and goes like, right, like this. It's like really big one. But it only takes a tiny little bit to push a little bit, right? And all you have to do is push them just a little bit to get heat, right? You're only trying to raise the temperature a degree or 2. It doesn't really lose heat very quickly. It doesn't really gain heat very quickly. So a little bit of solar heat goes a long way. A little bit of cooling goes a long way in terms of the BTUs. Okay, so on this one, we started out at a 10.3. Oh, let's talk about it. 8,000 square feet. The investment here was $125,000. Same cost of energy and energy inflation, 10.3% inflation return year 1. Now, if you're a nonprofit organization like this that relies on donation, and you're setting up an endowment, right? And somebody's going to give you $100,000 that's going to stay in the bank and going to earn you money every year to actually run your operations. You can look at this like that and say, wow, for year 1 I'm earning 10%. Not many endowments earn 10%. You can see the numbers climb. They're out at 22% by year 40 with a 15% annualized. And you can see that was a savings of some number, I can't remember what it is, about almost $800,000 for them over 4 years, which is very significant when their operating budget, I think, is, I can't remember, I think their operating budget is about $70,000 a year. So these kind of arguments are what it takes to get this market adoption. And once we get these things up and running, this is the dental office here. You can see 5,000 square feet. Now this dental office, interestingly enough, when we did our analysis, we only analyzed energy. We are in the process of working with them on the process load, the dental equipment, which is a very heavy user. And so we assume no savings in lighting and no savings in process load. And you can see we started at a 7.8% return, and up to 16.17% by the end. A savings of, well, 300,000 roughly. And what's interesting here is this is a practice of 3 doctors that have been together 30 years, and they're changing generations. So Dr. Lynch has already retired, his son's coming in. Dr. Zicky, his daughter is studying dentistry, and she'll be coming in about a year and a half. And Dr. Singleton, he's got about 10 more years of practice, so he's hoping one of his kids will go in. But Dr. Zicky said, this is a no-brainer. If I was doing this new building and selling the practice, I wouldn't invest in it. He said, but this is my kids. That's money in their pocket. So it was really kind of neat when we were going through this process with them. This is the Center for Energy. This was our school building. This building was completed in 2010. You can see it's just a small building. It's a freestanding building for advanced study environmental science students, and it's a LEED Platinum building, or we haven't gotten our certificate award. We're almost there with it. And it's got every bell and whistle we could think. The neat thing about this is they're using this building to underpin the entire school system's basic learning with sustainable ideas. So instead of Janie has 5 apples and Johnny has 6 apples, and what percentage better? When they teach percentage, they say, well, we have a tracking array of so many square meters PV, and we have a fixed array, the same square meters. How many square meters per square foot? What percentage better? So, and that gets, we've got rainwater, we've got gray water, and we've got recycled material. Just about everything you could shove into this, we did, and it's all monitored. And so, it's a pretty cool project. We worked on it about 7 years before we actually got under construction. So this started with a 9% return on investment, and you can see climbs to almost 20% over 40 years. Savings of $175,000 to $150,000. You can see this. The past best investment was only $25,000. It's nothing, right? I mean, for a little building, that's what it should be. And this is our first year in usage. I threw this in. This is from another presentation. But this is what our standard building, we used 31,000 kilowatt hours. Our predicted was 10,686. We used 10,050 the first year. And actually, we used, from the meter, we actually used 6,000 something. But because we had some site-produced energy, but we wanted to look at, what was our gross usage before site creation. So we have, 3 little systems on the building. We got 2 1 kilowatt and 1 2 kilowatt unisolar up to the roof, which is a pretty useless system in my mind. But so we're not producing a whole bunch of energy. We just got a grant to install some different type of PV systems, so we'll be an energy generator by the end of the year. So pretty good, right? We've got a first year's data, and what we're seeing now is we're getting the first year's data back on a bunch of projects in the States, and they're all performing pretty well. So that's pretty good. The other thing is, I don't know if you guys have studied LEED, but they make you do a thermal comfort survey, and we had nobody dissatisfied. The worst we had was neutral. The reds are neutral. We had no dissatisfied. So that's pretty unusual in a LEED survey not to have that. So that was really great. So that's pretty exciting stuff, right? We got opportunities knocking and saying, let's go out and build some really cool buildings, right? I mean, we've got this amazing story to tell. We can save all kinds of energy, and let's go, right? This is really exciting stuff. We got no place to go but up. No place to go, right? Well, we got the technology, right? We've got fabulous building science that's been done over the last 30 years that we've learned since we first did our buildings that melted. We've got computer power that has gone out the roof, which is now allowing us to do all kinds of different simulations that we couldn't do 20 or 30 years ago, right? So we got this great technology that allows us to go forward, but everybody knows that technology has a dark side, right? And we got to be careful of this dark side. Because if we're not careful, the dark side is going to bite us in the butt. So we got to step back for a minute and think. Okay? As a person out on the edge, and that's what I consider myself, on the bleeding edge, because there's not many people stupid enough or wild enough to be willing to go put their name out there and do this stuff. You know, I want to be singing the praises. Oh, house is great. Everybody should be doing it. And I am. And I'm being very honest with you guys because you're all designers that are going to have to go out and do this, right? But everybody knows you always can't be a happy, good cowboy. There are bad cowboys out there. You've got to be careful of them. So basically, we got a lot of work to do as pioneers, and it means, you know what those are? Cow pies. We're showing a lot of shit, right? We got to do the work. And for those of us who remember the 70s, early 80s, we got to be real careful because there were a lot of experiments gone wrong. So that kind of temperance needs to be put into the whole excitement of this movement because, you know, in Austria they have 6,000 projects. So a few bad projects in that 6,000, and there are some, it doesn't water down the success. But for us, you know, we have 10 projects and one's rotten, you know which one the U.S. press is going to pick up, right? So we got to be really careful and really focus on what we're doing, understand what we're doing, and not just jump in and everybody and his sister. What's one of the good and one of the bad things about PHPP is that it made energy analysis accessible to a huge group of people that had never had access to accurate energy assessment. But while that's good, it also put a tool in their hands that's very dangerous if they don't really understand what it is, because it's an extremely powerful tool. There's a ton of assumptions that go into it, and if you don't know where you're going or what you're looking at, you can make a lot of mistakes. So, what are our imperatives now? You know, we just got to be careful, show a little caution. And first thing is we've got to remember that Europe is not the United States, right? So in Europe, there's a delta between the culprit factors. You know, so in the winter time, if it's cold, you put on a sweater. In the summertime, if it's warm, you wear light clothes. It was really made clear to me. I was at last year in Austria, and I was at this brand new passive house school, gorgeous school, and huge gym. I was talking to the architect, and I said, you know, what do you do in May when you have a graduation of the kids, and you have all the parents and all the grandparents and aunts and uncles and brothers and sisters, and they're all crammed into this auditorium, and they're watching the kids, because there was no, you know, it's all hydraulically heated. And he says, oh, we opened the windows and doors. I said, okay, so you sweat and smell each other. Not going to be accepted in the U.S., right? So we got to understand that in the U.S., our expectation is that in the winter, and now I'm sorry I'm not speaking Canadian logistics, so I'm speaking from the U.S., we expect it to be 72 degrees on the interior, and in the summertime we expect it to be 70, right? We're just spoiled, cheap energy. So the very first thing we got to do is understand that the PHPP was written for European sensibilities and for European comfort. So when you start doing an analysis, if you use the basic built-in assumptions in the PHPP, you're going to deliver a building that is comfortable in Europe. And if you think that a North American consumer will accept a European comfort range, I think you might be wrong. So I think, yeah, that is a really important thing to understand about PHPP and the assumptions going into it. The next thing is that Europe has very limited climate zones compared to North America, right? So the other thing that we have that they don't is humidity, right? Humidity is not a problem. Also, interestingly enough, neither are bugs. When I've been ordering passive house windows from Europe, getting fly screens is really difficult. There's none of that. We don't have bugs here. What are you kidding? The other thing is to understand the usage pattern of these commercial buildings, right? In a house, it's really simple. You have a family or whatever. But we have buildings that are going to change dramatically in their usage pattern. So you got to understand that, because what you find with these high-performing buildings is that a lot of the drivers of the design become interior heat gain of lights, people, equipment, and not so much heat loss to the exterior, heat gain in the exterior. So one of the things that we got to be careful of is that when you have something exciting and something new, you want to go out and just like do everything you can, but the world is filled with a bunch of really good ideas that went really wrong, right? So we just got to be really careful. we got to be really careful. And you guys as designers, I all want you on this high performance boat, but I want you to understand with your eyes open what you're getting into. So, as architects, we're generally used to thinking in this box, right? I draw this design, I hand it to Mr. Engineer, and he figures out what the load is and then doubles it and then crams all this HVAC in it. And, my electrical engineer doesn't care. He's just going to go by code and tell me how many watts per square foot. We just recently did a building where the electrical engineer designed it to 1.2 watts per square foot, and he thought he had done really good. We went through, put in occupancy controls, changed all the lighting, and got it down to 0.5 watts per square foot for the same amount of lumens on the surface. So, you got to think outside the box. You got to be creative, right? You got to open your mind to possibilities, because they're all out there and they're all within your grasp. But you got to be careful. Is nobody's going to grab onto this stuff if it costs a bunch of money, right? If there's a ton of premium for this that you can't get back, like in photovoltaic, why would you do it, right? So it's about market. Understanding your market, knowing what you can and can't do within that, and then creating something that will get market acceptance. Now, the other thing is that we have to be meticulous as hell, right? You don't want to end up using this huge bat, which is what the PHPP is, and then ending up with a lawn that's all patchy, right? You want to catch every little thing. So I highly recommend the Passive House movement. Has got some of the most sharp and dedicated and nerdy minds I've ever met. And as a group, I encourage everybody to interact on a collegial way, to share your thoughts. And I get phone calls from colleagues all over the country to discuss ideas, right? On my way here, I got a call from a friend who's designing a library in Fairbanks, Alaska, and we were discussing mechanical concepts of how to deal with this and that. So, it's not about can I do this better than the other guy, or can I, this is all about we as a group, and we're a very small group right now, need to succeed in every project we can that we do. And so as a group, we need to support each other and do everything we can to share the knowledge and share the expertise. And if Russell has expertise in something that I want to know about, I want to be able to call Russell and not have to spend hundreds of dollars to talk to him on the phone, and same with him with me. And that's just the way the community needs to be kind of working initially. Now, once this gets to the old path, it's going to be a little bit different story. But remember, we're way out of the leading edge. That's it. Any questions? No?
Are there any questions, specifics or broad ones?
I know I covered a lot of territory there.
So just wondering, what is it that is stopping us from having asphalt certified products such as windows or
marketing?
I've
I've got 3 window manufacturers in the States that I've talked to that have very close to Passive House levels of performance, and trying to talk them into putting the investment into just getting a certified window. The attitude was kind of like, well, if I can't get 10,000 sales the first year, I don't want to do it. I know in the U.S. people are not very good at making boutique companies and with any kind of regularity. So maybe Canada's different, and maybe you guys are more creative, more innovative. There's a really simple way. Anybody here who's got $100,000 to invest and a little bit of intelligence could open a Passive House certified window factory tomorrow, right? Because in Europe, you can buy your window. But typically what happens is they have a little shop, and when you build an opening, you build your opening, then a guy from the shop comes out and measures the opening, and then he goes back to his shop and he makes his window, and then he comes out and he installs the window, right? Well, the way that the Passive House Institute in Germany has dealt with that is, yes, they have whole windows that are Passive House certified, but they also have Passive House components that are certified, right? So Vecca is a huge PVC extruding company. I approached a company down in Virginia where I live who sells Vecca windows. They just don't sell, they don't use the top line Vecca Passive House. And I tried to convince them, buy some Vecca passive house product, bring it in. You already have all the equipment to cut it and weld it and do everything you need. And I couldn't convince them just to buy so you can buy the components. You can buy the mullions, you can buy the jams, and then getting the glass is easy. You can get that from anywhere, right? So some little person, somebody, I mean, literally, if you had $100,000 worth of equipment, you could open up a passive house certified window factory. So I think it's just vision and market. It's cart before the horse. Right now we're doing a project in New York. Because I'm doing these commercial projects, I'm getting calls to consult around the country in the U.S. And I'm doing a project on the larger stuff. And I'm doing a project that's 40,000 square foot BMW showroom. And what the limiting factor is curtain wall. Right? There's 20 some manufacturers in Europe that make passive house certified curtain wall. Just gorgeous stuff. But nothing in the U.S. And even like there's Schuco and Rayco, which are common companies in the U.S. But they don't carry the passive house curtain wall. And trying to just get it from here to here in the same company is like pulling teeth. It's worse than pulling teeth. So, there's but that's part of being out on the edge, right? Anytime you're out on the edge, and I've been there a while, you're always fighting these kind of things.
What are the components of passive huts in terms of insulation? To get R30, do you use foam? You foam out 2x6 cavities?
I really don't use foam in any of my projects. I personally have a philosophical problem with foams, but there's no prescriptive anything, right? You can build any assembly you can come up with that makes sense. I kind of believe personally that you try to go for the most environmentally friendly assembly that you can afford rationally, so. But the other piece of that is the affordable part, right? So what we're building right now for our houses, I mean, it's like super simple. It's all based. Do you guys know the Cohen Climate Research Center in Alaska? Do you guys follow that?
I don't think. No, it's not very common.
No, really?
Yeah, sadly.
Sadly, yeah. So they came up with a system that our residential system is kind of based on. It's really simple. We just build a stud wall, right? And we put our air barrier, which is that air tightness, 0.6 air changes is like super important for passive house, right? That a lot of the magic of passive house is that air barrier. So in philosophizing about it in my brain, I kind of said, that air barrier, I don't want it to be inside and I don't want it to be outside. I want it to be in the middle of the wall because I don't want people messing with it, right? 10 years down the line, 30 years down the line, I don't want people to be able to poke holes in my air barrier. So we've just been using really simple product called Zip Wall. Do y'all have that product here? It's an pre-coated OSB. You use tapes to seal the edges.
I've never seen it.
Really?
Anybody else seen Zip Wall? It might be marketed under a different name, but
it's I forget which manufacturer makes it. But anyway, it's a really simple system, been around a long time. And so we put that on the outside of our stud. We're either using 2x4 or 2x6. And then we use an exterior insulation on that. Either a rock wool insulation or a EPS insulation, and that we're able to deliver very inexpensively a product that has no thermal bridging at all, because we're not like if we're using the EPS, we use a product called Nail Base, which is EPS with an OSB face on it, and it's like a SIPS panel lacking one side. And when you put it up, you don't have to use the 2x. See, that's one of the problems with SIPs is that you have to use a 2x or have window openings, the door openings, you end up with this thermal bridging problem right there. So by using the nail base, you eliminate all that. You kind of wrap the whole thing in a warm cozy. And then we use cellulose in the attic typically. And then depending on the client, we try to push for cellulose insulation in that frame wall on the inside. But sometimes our clients don't want to pay for cellulose, so they'll go to a batten insulation if we have to. But it's all about cost. Like, you can get really fancy with your stuff. There's also one other piece of this, right? And as a builder, I know that no matter how good you do as an architect, if it can't translate out in the field to like John and Juan, who are actually installing it, it ain't going to happen. And to get the 0.6 air changes, you're talking about a level of construction attention to detail that most mechanics in the field are not used to delivering. So one of the really key things is that you need to be able to design a system that's really simple to implement and that's as idiot-proof as you can get, because you'll definitely get the idiots, right? You just got to make sure that you got it proved, right? So I've seen some details that just like are beautiful details, but you look at them as a builder and go, they'll never ever get it implemented. At least not in my part. I mean, maybe if you got German workers doing it that you don't want to be very precise and make all those caulk beads at 3/4 of an inch and perfectly straight, you can do it. But in Virginia, forget it. You know, I mean, it's hard enough getting people to just follow simple instructions.
So, Jaime?
Yeah. So you mentioned that you recognize the fact there's a difference between set points that are used here, set points that are used here, and the climatic zones, and all these other things. You also mentioned that the PHP is being designed sort of to meet that sweet spot between the initial investment and then what it does in terms of insulation and air tightness and stuff like that. Obviously, those things will shift if we're talking about different climatic conditions and different set points.
They don't really shift, right? That the general overall the overall point is that they're basing that kind of point on the heat capacity of air and where they can get that energy balance, so that doesn't change. So when you're trying to hit that 15 kilowatt hours per square meter annual demand, you're actually getting to a point which you can hit in any climate. I mean, we've built in the U.S. We've built and have had monitored buildings from southern Louisiana through Fairbanks, Alaska, all hitting that same energy. Now, it's really, really difficult in both of those climates, but you're able to do it. And if you look at some of the Scandinavian countries, they have actually, like in, I think it's Sweden. Yeah, I believe it's Sweden has 2 different standards, one for above the Arctic Circle and one for below. So there's been some talk in the U.S., I think one of the things that I'm motivated by, and a lot of the initial people that are in this movement are motivated by, is making exceptionally good buildings that perform over time. Okay, if I build a building and it uses 16 kilowatt hours per square meter, so it's not a certified passive house, but still it's 3 times better, 3.5 times better than standard construction. We've done a good thing, right? We build a building that's going to perform and perform really well for the owner over time. If we build a building that uses the right type of building science where the walls are not going to melt, right? Then we're doing good things for our clients. And like the whole thing about Passive House is that it gives you an accessible tool as an architect to inform your designs that allow you to design smarter. Right, and it's not so much. It's not like LEED, where it's like I want all these points and I got to put extra money in to make my whatever bike racks or whatever. You know what I mean? It's like it's not prescriptive. It's purely kind of all here. So it only is limited by how creative that you can be, and that's really the cool part of it.
Right, but when we're talking about the cost efficiency of your assembly, that depends on the systems that you need to have in that assembly, right? So the cost efficiency is much better in a warmer climate than when you're in a colder climate.
That's true, but then you've got other issues. And actually, when you look at your numbers, actually, and speaking from experience, the insulation is not the expensive part.
What is your temperature range that you're working with on these projects? It all looks,
we've got 4,500 heating degree days where I am, and about 1,200 cooling degree days, and that's about. One of those projects has maybe 5,000, but that's I don't know what you guys have here.
That's about right.
It's about the same. Yeah.
Really?
Yeah.
No way.
We get tempered by this thing we call the lake.
Oh, wow.
Quite a bit.
We don't quite get as cold as you guys, I think.
Yeah.
We do get it, but it's much shorter periods.
Yeah, it's a little longer, cooler longer, whereas we're colder.
Right on.
Yeah, we're about 4,400.
Really? 80 days? Wow.
Now, the reference point may be different. That's the only thing. We're talking 18, they may be talking something slightly 18 and a half. That would
Yeah.
be a little bit.
We're 68. Is that 18?
So that's 18.
That's 20. 68 the reference. So yeah, there might be. There's a bit of a climate thing.
Yeah.
So you haven't made any adjustments to your requirements of the HPP in order to whatever climatic conditions.
No, and that would be up to the individual designer to make those assumptions. And that's where understanding the program is so critical, where you can really make a lot of mistakes by not understanding the assumptions behind it. And one of the nice things about PHPP is that it's all written in Excel, so you can go in and look at all the formulas and look where they're deriving their answers from, so you can kind of understand, if I do this, what else is it going to affect? Because you may reduce the R value to make your heating work, but then your thermal comfort may go up the wall. Right? I mean, you may end up with an interior surface temperature of 60 degrees or 58 degrees or 55 degrees, and that's not, on your coldest day, and that doesn't meet your criteria of thermal comfort and whether or not that's important. I mean, I had this long philosophical discussion with another colleague a couple weeks ago about passive house certified windows versus non-certified windows. And we had gone and tested some non-certified windows, and my big point was about interior temperature of the frame, that it wasn't about the performance of the window as much as the interior performance of the frame. The reality was, the point was valid, that this thing was going down a little colder than the thermal comfort guidelines of Passive House allows, but the reality is it was performing a hell of a lot better than anything standard would have performed, and we're only talking about inches of tiny degree differences. So you're really talking about kind of esoteric arguments at that point. So if you're talking about affordability and delivering a good product, this gives you a frame of reference with which you can kind of adjust up and down to optimize your envelope.
Are you interested in taking the why 15 just for the sake of 15 because it was developed in a sort of Central European climate versus the North American context?
A little bit. Well, the presentation seemed to hint on the fact that these numbers were thinking that that's where the sweet spot happens between cost efficiency and as a distillation or whatever.
Yep.
20%, right? So if that's where the numbers come from, that will shift up and down, right?
They're on the North American agenda, and which means on our agenda because we're on the tech committee. We're looking in the next couple of years at the idea of where you're getting from and shifting the number and thinking what's more justified for the North American context. So that's on the radar. The reason everybody has stayed with what it is now is because up to now, if you wanted to be certified stamped, you needed everything to go back to Germany, and that's the number. So and what Adam's saying is, if you build this and you're just off of it, it's still an incredible building.
Yeah, exactly. And that's what I was saying about using it to inform your design. If you're a designer, right, and you're trying to figure out what's my energy balance, well, the very first thing you realize is the one thing you can't predict is occupant behavior, right? So, yeah, so there's a ton of assumptions in every simulation software about plug loads. The reality is, plug loads are highly varied depending on how many and what type. And I mean, just the dorm was a perfect example. I mean, when we started looking at dorm plug loads, was there one refrigerator, no refrigerators, two little mini fridges? What was the efficiency of those? Did they have a gaming system, a TV, a printer? Did they have two printers? I mean, you start going through everything that a kid can have in his dorm room, and all of a sudden, you're having to cool that room all the time.
We have tea kettles in this building. One per student, it seems sometimes. Sometimes they all go on at once and the things get tripped. So
yeah. So anytime you're doing modeling of any sort, there's as much art as there is science in that, right? And it's the same with design and as an architect, if you're designing, like for me, as an architect / builder and a guy who makes his living by building buildings and getting paid to build buildings, if I don't design things that can affordably be built within the budget and delivered with a certain expectation of what, if I say that the energy is going to be X, it better be X to my clients, this is a tool that I can use to inform my decisions as a designer. When I sit down and I start thinking about what's this building going to look like, I already know where I need to be at the end in terms of dollars and cents, right? So what this program really allows me to do is to fine tune what's the best way to optimize that. And if I'm telling somebody they can get a 60% energy savings, then I want to pretty darn sure I can get a 60% energy savings, and that's a tool that can help me.
Last two questions, Stephen, and then
yeah, just could you maybe address a little bit, going through this huge condo boom in Toronto? How do you see, how are they dealing with that in Europe? Are they doing any high density like towers or?
Oh yeah, and
Like,
that's tons.
Is that coming soon, or like is that kind of the future of it?
Well, I mean, like I was telling Russell at lunch today that I went and visited with a developer that was redeveloping these 20-story towers, condos. Well, they weren't condos; they were actually low-income housing. But I tell you, low-income housing in Austria is way nice. I mean, it's way nicer than a lot of like regular market rate stuff here. And they had done one already. They were in the midst of doing another, and they were getting ready to do the third. And they had like this system down where they didn't even have to hardly bother the occupants to do it. But the thing, like the condo versus the low-income stuff, like the condo, you're going to pay your own utility in the condo, right? So where's the condo guy's incentive to spend 8% more? It's not, because that fits into their property. They're not going to get any. If they tell you you're going to use 40% less energy or 70% less energy, when you go to buy that condo, it has nothing. I mean, unless the market recognizes that, it's still market rate. If it's going to cost you $250,000, it's going to cost you $250,000 no matter what the energy use is. And then if you end up spending $500 a month in the wintertime because you have all glass and it's crappy glass, you're tough luck, right? Because whoever asked that question. So, I personally don't see that market until it's mandated. That kind of speculative market. But I think you guys are on the edge of a bust. So, I mean, this when I see around here, I've seen in a lot of other cities, and I'm like, man, there's no way this is sustainable. So, don't buy a condo right now. You're going to be able to pick them up in a couple of years for nothing.
Already sold out.
Huh?
It's already been sold out.
Yeah, I know, but they're building like crazy.
Well,
I don't know where you are in the cycle. I'd have to look at it a little, but I know you're in the cycle. You're in the bubble.
yes.
Yeah.
Actually,
Yeah, but I don't know where in that cycle. But that cycle goes.
they're on the top. Toronto would be the best and the high-ranking. The 133 high-rise building is on the construction right now.
Everyone sold out.
Actually made it on top ranking as per the city of Toronto. October, what do you call it? They have a study and they counted that. Actually, Toronto is on the top.
Yeah.
133
That's crazy.
high-rise.
Yeah, where's a lot of money coming from?
I'm not sure. You tell me.
Yeah, you tell me. Are people speculating on them here? Are people going in and buying them?
People from outside of the country buying it, predominantly Russians and
So they're buying them as speculation.
yeah,
Yeah.
and immigration. There's a lot of immigration to the city.
150,000 people. 80% of the Toronto every year, so they have to have a place to live.
Yeah.
And they bring money though, so basically that's where the incentives are.
Well, let's hope it keeps going. But I mean, it doesn't seem to go like that everywhere. I mean, maybe this is just an incredibly growing city.
It's amazing that you see the number.
Yeah.
All right, Monty.
Actually, my question is similar about the multi-level, 5, 6 stories. Have you worked on anything like that?
Yeah, I have. Like the dormitories, 4 stories. Those are really easy buildings to make work because the skin to volume ratio is really good, especially if you look at an individual unit. You end up. Those are actually, the cost delta on that dorm was less than 5%. Passive house versus non-passive. So
The way that you approach the design is a little bit different to meet passive house on.
actually, we were dictated. That's the thing is that we were dictated. We had to use the exact same design as the building next door. So we had no choice on elevation. We had no choice on massing. But nothing. Orientation, nothing. I mean, all that was dictated. Construction style was dictated. They're both modular. So I had to chip around the edges, right? So that's what's going to make that such a good study, is that we've got 2 exactly the same buildings virtually, just built with slightly different techniques. And what the housing, the guy who's like vice president of housing for that university said was, if this dorm works, you're going to have, you found the magic bullet. You found like what everybody's looking for. All these little colleges are all building dorms now. They all want to build quick, and they want to build cheap, and they want to be low energy. So we'll see. That's what we're counting on.
Thank you very much.
Thank you guys.